Hi everyone, I'm Kaihui Gao from Zhongguancun Laboratory. Today I will present RedTE, mitigating subsequent traffic bursts with real-time and distributed traffic engineering. This is a joint work with Fei, Songtao, Dan, Li, Congcong, and Yi. As you know, internet traffic is bursty, and traffic bursts can lead to queue build-up or even packet loss, bringing the jitter of network latency. That would hurt the user experience of latency-sensitive apps. Mitigating the impact of bursts in a cost-efficient manner is crucial for ISP, where the common practice is to double the capacity when the average link utilization is greater than 50%. But the strategy is cost-grained and not cost-effective. How come with the traffic bursts? Firstly, the sending rate of a flow may increase sharply due to certain traffic demand, including applications-based nature and batched operations in the network stack. What's worse, when multiple bursty flows compete for the same path or link due to load imbalance, which will cause a violent burst and congestion in the network. So bursts are unpredictable and usually occur on a millisecond timescale. Those make it very challenging to mitigate bursts. There exist two traditional approaches to mitigate traffic bursts. Firstly, end hosts smooth out the sending rate by using flow control or traffic shaping, but they are unfriendly to ISP deployment and cannot avoid traffic collisions in the network. Secondly, device local traffic managers in network can distribute traffic among multiple paths to avoid congestion. However, both of them are not aware of global traffic patterns and can be stuck at a local optimum. So ISPs are looking for a burst mitigation strategy which has global perspective and functions within the network. So we start looking at traffic engineering methods. We think TE is uniquely equipped for burst mitigation because it works based on the network-wide information and targets the network-wide performance. But TE is usually ignored previously because it had slow decision-making speed. Compared to the duration of bursts, the control loop of TE operates on a larger timescale. Because the control loop of centralized TE has 3 steps. The first step is data collection, where a centralized controller gathers network information from routers, including network topology and global traffic demand. This step usually costs seconds long. Then, the centralized controller computes the optimal routing configurations, which outputs the splitting ratio on predefined paths with the goal of minimizing the maximum link utilization. It usually lasts seconds or minutes long. Finally, in the decision deployment phase, the centralized controller sends out these routing configurations, and these routers update the route table in data plane. It also takes seconds long. Then, why control loop latency is so important? We conduct experiments to show how different control loop latency would take effect on TE performance. We choose linear programming algorithm and the TE method, and simulate different control loop latency by controlling the interval between information collection and decision deployment. And we use public packet trace from WIDE, a major backbone network in Japan. The packet trace have 50 millisecond level bursts, and we use 2-1 topologies. The results indicate that when reducing the control loop latency from 25 seconds to 50 milliseconds, the performance of the TE system is increased by up to 47%. The number of events where link utilization exceeds the capacity threshold is also decreased. Why shorter control loop latency brings better performance? I try to give a quantitative analysis. For the same burst, if TE speed is too slow, for example, control loop latency is bigger than the burst duration, bursts are gone before TE takes effect. If the speed can be faster, TE system can timely react to burst, distributes the burst traffic over different paths before bursts lead to congestion. And after the burst is identified, the faster we respond to it, the smaller the MLU of the network. So we claim that in order to effectively mitigate burst-induced congestion, the control loop latency must be close to the timescale of traffic bursts, or even smaller. Then our research question is how to reduce the control loop latency of the system to the burst timescale. Even though existing T-works attempt to reduce the control loop latency, but they still do not meet the requirements. For example, centralized LP-based TE and centralized machine learning-based TE focus on accelerating the computation phase, still spend seconds long time in data collection and decision deployment. In contrast, distributed TE makes decisions only based on local information, has faster speed in these two phases, but they suffer from a multi-step adjustment process to handle bursts. The convergence time is at least seconds. In short, none of the state-of-the-art TE works achieve response time on the millisecond level. Inspired by previous work, our goals are twofold: reducing the control latency to the burst scale while maintaining performance comparable to that of centralized TE systems. To this end, we present RedTE. Firstly, it follows the distributed TE idea, which makes decisions based on the local information. Besides, the second design choice is using multi-agent reinforcement learning. Even without access to the global information in the inference phase, RO agents in routers can be trained for a long time offline using the global information, and attempt to make the global informed decisions online with locally information. In other words, if a similar situation has happened in training, the routers can learn from past experience to output optimal T decisions, avoid a slow multi-step convergence. This is the architecture and workflow of RedTE. RedTE routers are deployed only at the edge of the network. This makes deployment easier. The network transmission paths are predefined and implemented by segment routing. At each control loop, each RedTE router collects local information, including the link utilization, bandwidth, and the current traffic demand vector, and then conducts the inference to get the routing configurations, that is the traffic splitting ratio among multiple candidate paths. Finally, it will deploy the splitting ratios into the data plan. On longer timescales, the controller retrains the model offline. Each RedTE router reports the traffic demand to the controller and periodically downloads the I/O model. But in order to meet our goals about speed and performance, we still face three challenges. Next, I will describe these challenges and our corresponding solutions. The first challenge is how to ensure collaboration among all agents to achieve global optimization. We model distributed TE system as a cooperative multi-agent system. But since each router only has local information, how can they cooperate to achieve the global optimum instead of each making greedy decisions? The essence of the problem is that even if we set the global performance as the reward function, agents cannot figure out its all contributions to the global objective, resulting poor cooperation among agents. To address this problem, we borrow the idea from the cooperative game field and applies the MADTPG algorithm to train the IO models. MADTPG aggregates the process of all agents into a global critic model and distinguishes each agent's contribution to the global reward. That is, the critic has a global view and can judge the actions of each agent. As a result, through separate and precise feedback, agents learn to cooperate. Second, in TE scenario, traffic is continuously injected into the network, which is called a traffic-driven environment. That means the state transition process is not only driven by the agent's action, but the arrival of network traffic. Since the traffic arrives randomly, so the reward is also random. Means a good action may receive a very small reward because a new TM sequence with a high load arrived. So training takes a long time to converge. The key to solve this problem is that IO models need to use short-term memory to learn the long-term TM evolution patterns. Traditional training methods replace all TMS sequentially and again. TMS are always new to the IO model and arrives randomly, so it takes a long time for the model to converge. Instead, we fix a shorter TM subsequence and replay it multiple times till model convergence, then switch to the next TM subsequence. In this way, agents would experience the same TM multiple times in the shortened memory, and the effect of the new incoming TMs can be mitigated, so the model can converge faster. Then, we find that the decision deployment time becomes the new bottleneck. In that phase, row tables with many entries need to be updated. For example, for a row table with 80,000 entries, it takes almost 1 second, accounting for 60% of the total controllability. If we reduce the number of entries in the row table, it would sacrifice the TE performance, because more entries in the row table will enable more accurate traffic splitting. Our insight is that there are many equivalent update policies with similar splitting effects, but each brings different time cost. So we can decrease unnecessary path adjustment by designing a deployment-aware reward function, where both TE performance and the number of updated entries are considered, making it possible to update only the necessary fewer entries at a time. Okay, we implement whole the RedTE system, including a centralized controller and RedTE routers based on Barefoot Tofino platform. We also deploy the system into a real WAN, consisting of 6 cities and spans 6 data centers. In our evaluation, we test the TE solution quality, the number of updated entries, and the controllability of RedTE with these baselines using for WAN topologies. Firstly, we show the overall TE performance of RedTE. Compared to other systems, because RedTE can make the load balanced in time, it reduces up to 42% of the average normalized MLU. RedTE reduces up to 75% of the maximum queue length. In the real WAN, benefiting from the optimization of the entire control loop, compared to other TE methods, RedTE reduces up to 30% of MLU and 54% of maximum queue length. Then, let's break down the performance of RedTE. We test the contribution of each of the 3 designs to the TE performance. By introducing MADTPG in model training, all agents can cooperate with each other to achieve global optimization. RedTE reduces the MLU by up to 14%. By employing circular traffic replay, the model converges better. RedTE reduces the MLU by up to 8%. By using the proposed reward function, RedTE reduced the number of updated entries by up to 87%. Besides, based on the fine design of the distributed architecture and the reward function, compared with other TE methods, RedTE speeds up the control loop by 200 to 300 times. Moreover, RedTE firstly achieves lower than 100 milliseconds control loop latency in a large network. In summary, we firstly find that the control loop latency is the key factor in applying TE to burst mitigation. And to address the problems faced by MLL in the distributed TE scenario, we propose 3 designs. Then, we implement and deploy RedTE in a real one. Evaluation reveals notable improvements compared to existing TE solutions. The control loop latency is lower than 100 milliseconds and has a 30% reduction in MLU and a 54% reduction in maximum queue length. That's all. Thanks.